Alright, continuing. So I left off somewhere. I didn't finish the analogy, I suppose, of the example of gravity going through me, before the phone call. Anyway, and the fact that it's not pushing me, literally. It's just changing the arrangement of my matter and making it gain velocity going down. And then the ground stops me, which is that velocity, that extra velocity that my atoms are now trying to go down, or there are to some extent, and they meet another force as they hit the other matter that's pushing back up. And that where this essentially happens is I end up bouncing on the surface of the earth. My molecules are bouncing. They're not allowed to go down because they get the forces, the gravity they're expelling internally, the arrows they shoot out as they interact with the world, the ones they exchange, the ones coming out the side, collectively end up bent the opposite direction as the forces end up twisting the arrows back in the opposite direction, the equal but opposite reaction kind of thing. The two arrows that collide and go their separate ways. The force going down ends up colliding into a force coming up. And essentially, because it's also doing the same thing, bouncing on the surface because of the pressure that the gravity is applying as you get closer and closer to the center of gravity. The more and more gravity is blocked, more and more gravity is imbalanced and hitting. It's not even the center, you're at the focus of the gravity. It would be wrong to say the center. It's just the focus, and the focus is the thickest part. Any thickness. But obviously the thickest part has the most gravity. The blocks the most gravity, which in turn creates the gravity. It's the imbalance. It's always an imbalance that changes disposition. But the key fact to understand is that you're not pushed by gravity. Gravity actually reorients the matter in you to have a wobble in the direction of the imbalance in gravity. Alright, good enough. You do have to, require some careful language here. Just a remark, the other videos already got 5 thumb down. I just wish people would leave a name or something, if you're gonna, just because in the end, I would like to, I would like if you'd make the actual video saying, I know you're wrong, or say something explaining this hostility, yes, to a scientific theory, merely presented, right? It looks a little bit like the persecution throughout history by religious nuts and stuff. Scientists aren't supposed to be afraid of somebody speaking words about an alternative theory. And it seems like you're all afraid. But anyway, it seems like the reaction of cowards and people who have something to lose somehow. It seems you should have something to lose before you would hit a thumbs down button here. Especially, again, there's no counter argument. If somebody's making a counter argument, if you even posted a link to some brilliant counter argument, that would mean something. Some demonstration of why I'm wrong. But it's not, like I said, I don't mind. It'll just make the crow pie I'm going to force you all to eat in the end that much more satisfying for me to serve up. But anyway.
Well, you can't talk about how strong gravity is by saying I take a lump of such and such a size because you chose the size. If we try to get something that nature produces her own pure numbers that has nothing to do with inches or years or anything to do with our own dimension, we can do it this way. If we take the fundamental particles, such as an electron.
There. So, I don't even think in his day there was any reason to conclude that an electron was a fundamental particle. It's a small particle, but there was nothing about it. When you add up the amount of energy that's in an atom, just composed of proton, neutron, and electron, there's so much energy. It's kind of hard to imagine how exactly it could be fundamental when there's that much energy that can fly out of it, that many photons. I think an electron has 500 gamma rays in it. It's not huge by comparison to the proton, the neutron. Those are huge by comparison. That's where all the, in a nuclear reaction, that's where all the photons are coming from. Is the protons flying apart, I believe.
Any different ones will give different numbers, but to get an idea of the number, take electrons. 2 electrons, a fundamental particle. It's an object. It's not something I don't have to tell you what units I measure in. It's 2 particles that are fundamental particles. And they repel each other inversely as a square of the distance due to electricity. And they attract each other inversely as a square of the distance due to gravitation. Question.
See, he just said something there that, again, maybe he's not too careful. No one's ever felt or tested or analyzed or in any way seen the gravity between 2 electrons. Ever. He's just speculating because they have mass, they have gravity, and therefore their gravity is the same as our gravity. Now, obviously, if they're made of this condensation, this collection, okay, their gravity is going to be more significant just in terms of the fact that it's all or nothing. It's not measuring the empty space between these bits. So there's no accounting on that scale for that empty space. And what it is that's creating this electrical effect that seems so powerful is in fact just gravity, but it's polarized. So electricity and magnetism has these angles. I mean, electricity has these angles. You know, from 45 to 0 as a polarized angle. They're linear this way, and magnetism would have the 45 down to 90, and that's essentially all polarization is just a rotation of those angles. It's all the angles are in there, and you're just changing the orientation. It's the same lines, the same shape. This is the same as this in terms of polarization. What it counts is how vertical to horizontal you are. So you can do all the vertical to horizontal vectors in any one of the quadrants, and it's all the same thing in terms of a vector. But anyway, and that's what's creating those phenomenons. But it's still gravity. It's just that gravity's different on that level. First, it's double gravity because you're focusing, you're filtering for specific kinds of gravity based on polarization, which means you can have it so one polarization is invisible, that is, there's no blocking of that force, and the ones that are polarized correctly you block twice as often, kind of a thing. But regardless, it still doesn't get to the point, but I'll let him finish and then I'll get to my point that I've made before, but I'll just
What is the ratio
reiterate.
of the gravitational force to the electrical force? And that is illustrated on the next slide. The ratio of the gravitational attraction to the electrical repulsion is given by a number with 42 digits.
Okay, so the great thing about this is really an illustration of the density issue. So the density between an electron, I would say if you went one level deeper is where you'll find the electrical force. The electrical force isn't in the electron, it's in the quanta making up the electron. So you have to go one level of density lower to appreciate it. It's not the electron, it's the stuff inside the electron. And the stuff inside the electron still has space in it. And what this number represents is how much space there is between, by ratio to relevant quanta, between the quanta inside of a electron based to an object the size of me. How much space there is now by comparison, the empty space. And so that's sort of the irony here, is that what matter is really doing isn't consolidating quanta. It's collecting them with a ton of empty space. So we're really not densities of quanta. There's more quanta in the air, theoretically, in the space, in empty space. There's these gravity. There's more gravity in gravity. There's more quanta in gravity than there is quanta in matter. Matter has more empty space in it. So the density of little arrows, there's more of it in the empty space, in space, than there is in matter. So matter isn't a concentration of quanta. It's an arrangement, and it's an arrangement that creates empty space. So I think that's sort of interesting. But this is just the ratio, really, between the size difference. That's all this illustrates, is size difference. This is the size difference between the quanta in an electron and, say, a material body of our size, or even the moon size or the Earth size. The number would only be one more zero to indicate the difference between the Earth and a human. But that's how much empty space there is in matter on this level of the universe. Yeah, I think it's a good enough way to put it. So I shall be back. Well, let's just play you
It goes off here. It's all this is written very carefully out, so that's 42 digits. Now therein lies a very deep mystery. Where could such a tremendous number come from? That means if you ever had a theory from which both of these things are to come, how could they come in such disproportion?
See, so this is one of the things where if you really thought about it, you know, I mean, I think if they gave real thought to it, they'd say, well, the disproportion is there's complete impacts on that level, and there's very more space to quanta, probabilistically lack of odds of contact at our level. The force is much weaker, but there's much more space to travel through before it hits something at the big size than at the little size.
From one equation has a solution which has, for one, two kinds of forces, an attraction and a repulsion, with that fantastic ratio.
Right. And the attraction repulsion is it's complicated, but it's all repulsion. It's just that you're negating the opposite of gravity. Would be something that doesn't block gravity, shield you from it, but actually produces twice as much of something that you're hostile to, and that would create an internal pressure higher that drives things apart. But it's really just allowing pressure to get to a surface again. So it's just that there's more internal pressure than external in that case, because you've changed the polarization. But I don't think I want to do polarization in this video yet, anyway. But it certainly is explainable. And if you just take the polarization part out and just take out the force strength, it's still gravity, and it's gravity merely on the level that the gravity actually functions on, without the empty space created by the orbits. Yeah. Good enough. I probably should have continued this this bit. Is pretty good.
For such a large ratio in other places, they're looking for a large number. They hope, for example, that there's another large number. And if you want a large number, why not take the diameter of the universe to the diameter of a proton? Amazingly enough, it also is a number with 42 digits. And so an interesting proposal is made that this ratio is the same as the ratio of the size of the universe to the diameter of a proton. But the universe is expanding with time. And that would mean the gravitational constant is changing with time. And although that's a possibility, there's no evidence to indicate that it's in fact true, and there are several difficulties, partial indications that it doesn't.
Yeah, right, okay, the partial indications and blah, blah, blah. So anyway, he just basically said it in a different way now, because now we went to the proton, and we went to the whole universe. So comparing us to an electron gets you the number, and comparing the universe to a proton gets you the number. So that's sort of interesting. But anyway, so he's basically confirming that's where the number comes from, obviously because it matches, and it just has to do with the level of the force. You're on the force's playground, so to speak, when you're at the size of an electron. That's where the force really is. That's the force that's actually doing everything that we're doing. The Earth is rotating around the sun because its atoms, because its nuclear parts are being affected by gravity, not because the Earth is. The Earth as a whole is invisible to gravity. Gravity only cares about interacting, it only can interact with the nuclear bits. And so that's why it looks weak from here, but it's plenty strong on its own home field. Yeah, good enough way to put it. Alright, till next bit. Alright, I think I'll play this bit.
One is that Einstein had to modify the laws of gravitation in accordance to with his principles of relativity. The first was, one of the principles was that effects cannot occur instantaneously, while Newton's theory said that the force was instantaneous. He has to modify Newton's laws. They have very small effects, these modifications. One of them is, all masses fall. Light has energy, and energy is equivalent to mass, so light should fall.
Right. So energy is equivalent to mass is kind of tricky, okay, because mass is made out of energy. Energy is required to make mass. It's not the other way around. Mass doesn't make energy. So mass is as soon as you have created an orbit, you create mass. But without the orbit, there is no real mass. There's just energy. So light can't produce energy beyond the fact that it is energy. It can't be called mass because something is energy. That would give gravity mass. Gravity doesn't affect gravity. Light isn't bent by gravity. So let me just finish here.
And it should mean that light going near the sun is deflected. It is.
Okay, so light going near the sun is deflected. Yes, it's deflected because the sun is oozing a ton of nuclear particles, electrons, protons, ions, and that those ions, those elements of matter, are what the light is hitting and being, is the word for that, scattered. And the scatter we call diffraction. So near the surface of any body exercising significant gravity, there's a percolation, a steam, a bubbling of particles. Off my skin right now there's a bunch of particles that are released, and the electrical charges pull them back down. And they're just going in and out of that surface constantly. They're being blown out, blown back in, pushed back in by the gravity, and the gravity is the electrostatic charge. It's the same force, again, just polarized. But the point is they don't escape you. They just rise off your surface and or re-enter you in some other form. Like your heat, most of it does escape, let's say. Not most. A percentage of it does escape as infrared radiation. But much of it just comes off the surface and ends up going right back into you again. And so through the edge of anything's gravity, surfaces are active is the point to make. They're not hard surfaces. There is no such thing as a hard, pure surface where on one side it's matter and on the other side there's nothing. There's always a steam, a corona of some form of nuclear particle forming a radiation from anything, everything. Is there anything else I want to do that? So Einstein's theory is gravitational lensing. Gravitational lensing is happening, but it's not because of gravity directly. It's because of the plasma, the corona, created around gravitational bodies. That's what's causing the lensing. Especially active ones like suns that are radiating a ton of energy that ends up being reabsorbed by the sun. It doesn't acquire escape velocity. The particles don't acquire escape velocity. They don't leave the sun. They just blow out of the sun and are sucked back in again. You have all kinds of things like, man, I can just, why do I have to search for these words? They call the, you know what I mean, it's not only do they have tides, but they have those bursts of radiation. We have a name for them that I can't remember at this moment. Doesn't really matter. Solar wind, but there's another word for the spots and what they do. Anyway, the thing I just wanted to throw in here for a pointer on gravity is there's two ways things can be gravitationally arranged. You know, it's the standard one where something orbits something straight, and then there's this other more complex arrangement where two items end up orbiting each other in a spiral, like one chasing the other essentially, and the two are still blocking gravity. They're still being attracted, but there's nothing in their center of gravity. There's no matter in the center of their gravity, and so you can end up very complex relationships where an item will circle, and a classic kind of idea would be a figure eight, where one where they have, let's say they had opposite trajectories, they would end up, this is not a connected line, it's separated by space, but they would end up flowing through those two circumstances because they come at each other, but they don't hit each other because of their trajectories. But they're pulled back together by these internal forces, these electrical forces and magnetic forces. But regardless, just the simple part here to understand. And so there's these galaxies, in the big universe, and they tend to be the spiral type, where they're doing this kind of thing. Just quick little spiral kind of diagram around a center. But most of the gravity is really in these spirals. It's not like most of the gravity is here. Most of the mass, is in the center. It's in these big spirals, and these spirals have a balancing act. So half of the gravity might be for a big galaxy is not being created by the center sun, but is actually being created by an opposite mass. So it's like the Earth having another Earth on the other side of the sun, exactly opposite it, and less sun and more Earth. So the bigger that other object would be, the more it could be pulling us in exactly the same direction as the sun. It would always be between us and it, the gravity, and so it would be exactly like chasing the sun. Now, maintaining those orbits is the tricky part. If you made the other Earth bigger, you'd have to make the two things of equal mass, or you'd end up with a real problem where one would end up escaping or collapsing. And so it's hard to maintain an orbit that way, but you could end up with a very eccentric shape created by two bodies that are getting caught in each other's gravity. And again, that's a possibility for gravity. But what this indicates is these galaxies have kind of a limit to their size, and they always do have a little black hole here somewhere. But the black hole isn't all the gravity for the entire galaxy. The black hole is really just gravity to create some condensing here in the middle. It's almost like lensing again. You have these layers of density, and these layers of density are what's really that's gravitationally holding everything together. And what is interesting to understand is that these galaxies do not have unlimited size. They get a certain size, and that's as big as they can get, because the gravity sort of runs out. There's only so much gravity you can block, and that's another indication of how gravity is a something, not something built into anything, not a structure of space anyway. It's clearly a structure that runs out. Because it's when it runs out, it can't hold any more stuff. It can't create any more gravity, go bigger and bigger and bigger. So galaxies, there aren't any mega super giant galaxies. There aren't any galaxies that are 1,000,000 times or 1,000,000,000 times bigger than the smallest galaxy. There's a limit to how big they can get, because there's a limit to how much gravity can be created. Gravity being how big the imbalance of pressure can be. There's a limit to how big the imbalance of pressure can be, and that limits the size of galaxies. Okay, so I'll be back. Alright, continuing a little bit here.
On a small scale obeys laws so different, very different than things on a large scale. And so the question is, well, how does gravity look on a small scale? What is called the quantum theory of gravity? There is no quantum theory of gravity today. People have not succeeded completely in making a theory which is consistent with the uncertainty principles and the quantum mechanical principles. I'll discuss these principles in another lecture.
At least he calls them principles instead of rules or laws, because they're not established as anything beyond circumstance that exists, but completely unexplained circumstance. But they are explainable if you can get gravity down. So this is, and again, I'll just point out that they have been very good at looking through telescopes and very bad at looking through microscopes, so to speak. The microscopes are much more limited because of the need for light to reflect off of things. It's got a limitation in terms of the granularity we can see, where telescopes can wait 3 years to have an image resolved. They can look at space for days and wait for the little tiny photons, the tiny bit of light to get somewhere and resolve it. So they can see deeper, in a sense, than we can see with a microscope. And that limitation has skewed, the limitation from this center, we can see, something like 60% of that, and we can only see 6% going the other way. And that imbalance has created a perceptual problem where they haven't recognized that gravity does go down, and it goes all the way down to the littlest, tiniest bit, and that's where the real force is. And we're just calling a nuclear force, which gravity is, some other kind of force, because it's so distant from its origin. But that's its real origin. It goes all the way from the nuclear bit to the ends of the universe. It's the only force. It's the force. And it's just, we're not understanding. We're seeing it at tremendous different dilutions at different densities. That's probably enough. I don't think there's anything else here, and then we'll move on to part 2. Yeah, okay. So, till the next time. Till part 2. Yeah, okay. Anyway, he's beginning his introduction in part 2, mathematics and physics, and the point being made essentially is that mathematics doesn't deal really with the simple rules. It deals with the rules in the implications on large-scale permutations. So when you do something a lot, or a lot of a simple thing, you can create very complex circumstances just by doing simple things like a checkerboard. So I just play this a little bit.
Imagine an enormous board, a checkerboard to play checkers or draw. And if the board is very large, the actual operation of any one step is not mathematical. It's very simple if it's mathematical. It either goes one side or the other on a diagonal, or it reaches and becomes a king and can go backwards when it reaches the end. In other words, the statement of the rules are very simple and do not really involve any mathematics. But you could imagine that on an enormous board with lots and lots of pieces, some analysis of the best move or good moves or bad moves might be made by a deep kind of reasoning, which would involve somebody having gone off first and thought about it in great depth, and that becomes mathematics, this abstract reasoning. Another...
Okay, so just, so he's just giving examples of the fact that you can have very simple things that lead to very complicated things, and that math can formalize the outcomes. Say, give you an idea of what likely outcomes will happen with circumstances, what you put in and what you get out. And the formula is a reflection of the relationship of what's going to happen over its evolution through time, essentially, something like that. Well, anyway, that's a paraphrase. It's not terribly important, so we'll move on. Alright, I'll just play this bit. It's back to the FGMM R squared, this is the inverse square rule, which just basically does that 4 times half the distance, twice the distance, 4 times the effect, and vice versa, of course.
That's words, all right, and I didn't have to write the equation, but nevertheless, it's kind of mathematical, and we would wonder, how can this be a fundamental law? How can this planet out there look, what does it do? It looks at the sun and it sees how far away it is, and it decides to calculate on its internal adding machine the inverse of the square of the distance, and that tells it how much to move. This is certainly no explanation of the machinery of gravitation.
Right. It's the same joke you used in the last lecture. But anyway, and that's sort of the point. But it is a description of the relationship. And it's a description of what the relationship's always going to be with straight line force. Forces that have vectors that are straight.
So you might want to look further. And various people have tried to look further. Newton was originally asked, it doesn't mean anything, it doesn't tell us anything. He says, it tells you how it moves. It should be enough, I told you how it moves, not why.
Right, and that's sort of a good point, that, yeah, once you know what it's going to do, then that's mostly what you need to know. You know, you don't need to know why a bear is a bear. You just need to know what a bears do. You know, what does a tiger do? You don't need to know why a tiger is a tiger. But for the purpose of description of the bigger picture, evolution, this, that, and the other thing, all of that does require you to kind of know what the mechanism is to get that right, to understand DNA molecule and chromosomes and alleles and the chemistry of it. All of those things you need to sort of get right. If you start putting angels in somewhere, putting voodoo in somewhere, you can end up getting it all wrong because your premises of your system dynamics is all wrong. You put things in the system that don't belong there, and they will cause problems with your relationships. You won't be able to mathematically get it right either, eventually. But anyway, we'll move on. This is the Lesage bit, so we'll play this again and I'll rag on it again.
Running in, he suddenly explains gravitation. Suppose that in the world, everywhere, there are flying through us at very high speed a lot of particles that come equally in all directions. They're just shooting by, shooting by, shooting by, and once in a while hit us in a bombardment. But we and the sun are practically...
Okay, so the key concept there is particle and hit. And so the difference between what I'm arguing and that argument is that I'm not talking about something being hit. I'm talking about something exchanging directional information. A hit implies something breaks off. It implies something is moving slow and something is moving fast. And that's not happening. These little bits are all moving the speed of light. And when they interact, all they do is exchange directional information. They don't exchange velocity. They don't exchange mass. So there's no energy transfer whatsoever. There's just directional transfer. There's just a change in direction, nothing else.
Be transparent for them, nearly. But
And again, the change is invisible in a sense. The change is like the shape of an X, and you can imagine that the thing going one way is now going that way, and the thing going one way is now going that way. And it's the same X. They just went right through each other. But the trick is when they start doing this angular thing, that's the beginning of a box they're going to get trapped in, so to speak.
some hit, and so it's not completely transparent. Then look what would happen. If the sun is here, and the earth is here, then if the sun weren't here, there would be particles bombarding from all sides, giving little impulses by the rattle of these bang bang, the few that hit.
Okay, so giving little impulses. So again, this is a very intuitively, in that sense, he's thinking of it as matter hitting matter instead of energy hitting energy. And that's the key problem. It's energy hitting energy in the matter. It's not hitting matter. It's hitting the energy in the matter. And that's the key difference. There can't be a transfer because of energy, because it's energy hitting energy. And energy hitting energy can't make energy.
Which would not shake the earth in any particular direction, because there is many coming from one side or the other, from top from bottom. However, when the sun is here, the particles which are coming in this direction are partly absorbed by the sun because some of them hit the sun and don't go through. Therefore, the number that are coming from this direction toward the earth is less than the number that are coming from the other side, because here they have no opposition from no sun there. And it's easy to see, after some mental effort, that the further the sun is away, the less in proportion of all of the particles are being taken out of the possible.
Right, and so you can see just by these kind of diagrams of size, but it is really about density, but it doesn't really matter, that you can just do the inverse square thing. You could just draw this triangle of coverage, and that sort of gives you your inverse square relationship.
Possible directions in which particles can come. The solar size appears smaller. And in fact, inversely is the square of the distance. So there will therefore be an impulse toward the sun on the earth that's inversely as the square of the distance, and is the result of large numbers of very simple operations, just hit.
So again, he said simple simple operations, just hits, but they're not hits. If he would, all he needed to say to understand was to say simple operations and exchange of directional information, and then it all works. Then you don't have a heat problem, you don't have a momentum problem, you don't have a friction problem, you don't have any of those problems if you recognize it's not matter interactions, it's energy interactions.
One after the other from all directions. And therefore the strangeness of the mathematical relation will be very much reduced, because the fundamental operation is much simpler than calculating the inverse of the square of the distance. This machine does the calculating.
There you go. Now that's an argument I keep making to people. They keep saying, where's your mathematics? Well, the mathematics is already done. We already have formulas describing it. And what I'm giving you is the machine where you can actually draw a picture of it, okay? I mean, you can draw the picture. You can draw a representation of it and see it. And yes, it wouldn't hurt to quantize that into some sort of mathematical proportions to account for the levels of energy and all of that stuff, the numbers of these things and all of that, and that's certainly doable. To expect me to do all of it in a day or a week or a month is kind of a silly expectation. But anyway, it's continuing.
These particles bouncing. Only trouble with it is that it doesn't work.
All right, now see, this is the same guy who talks big about all this pursuing reality and looking for the truth and all of this stuff, but I think he was again, his analysis wasn't very physics sensitive. Wasn't sensitive to the fact that physics is more complicated than things hitting each other.
For other reasons. Every theory that you make up has to be analyzed against all the possible consequences and to see if it predicts anything else. And this...
Well, again, this does predict time dilation, and it unifies magnetism and electricity into, and even the nuclear forces, into gravity.
Predicts something else. If the Earth is moving this way, more particles will hit it from the front than from the back.
Right, so the problem here is that he's not thinking about the particles in here as being also moving the speed of light, and that they can't really move. Okay, they're already moving the speed of light. Everything's already moving the speed of light. All they can do is change direction. So a way to understand it or think about it is if I gave you a school of fish and I told you the fish can't eat anything, they can't get bigger, and they all go 30 miles an hour, and they're in a school and they're just swirling about. Well, when they're swirling about, they're banging into, let's say we just fill the ocean with an even layer of plankton. They're going to hit just as much plankton as if I moved every one, if I changed the direction of each one of the fish and had them all moving in one direction. They would hit just as much plankton if they're all moving like a laser beam in one direction. They'll hit just as much plankton as they'll hit swirling around each other, as long as we concede that they can't eat the energy. They can only bang into it, interact with it. And so there's no friction. There's no opposing for it. You can't speed up. As soon as you try to escape, as soon as you try to bang into more stuff moving the speed of light, you escape just as much stuff you banged into. There's no difference. You're ending up hitting just as much stuff. You can't hit more of a certain direction. The directionality is a fact that already exists. You can't change your orientation to everything else moving the speed of light. You can only get from point A to point B in a straight line, or you can get there in a crooked line, hitting a lot more stuff. But in the end, you can't change your relationship between the two things. You can't get there any faster.
If you're running in the rain, more rain hits you from the front of the face than in the back of the head because you're running into the rain.
So again, you have to think about rain running into the rain. It's a very different relationship that the quanta have to the universe than something you're making, you're freezing. You're saying it's in one place and now it's going to move. It's already moving. So all you're doing is changing the direction that it's moving in.
And so as the Earth is moving in this direction, it's running into the particles, rather, and running away from the ones that are chasing it from behind, so that more particles hit it from the front than from the back. And
like I said, I've done this more extensively in other videos, but the point is that can't happen, because as your photons end up, as your gravitons, your quanta, end up moving in a direction, more of them are going in that direction, and they just create head-on collisions, which are essentially invisible collisions. You won't be exchanging different directions, you'll just be flipping the direction, and so it's nothing. It's a non-event, just like the photons that'll never be able to hit you from behind because you're already moving the speed of light. So you're still interacting with just as much plankton, and the plankton can't do much about your direction because not enough of it's coming at a direction to change your direction. There's no difference in this stuff coming from the top and the bottom. There's no change in, there's no imbalance in the force affecting you to create a change in your velocity.
there would be a force also sideways whenever there was any motion. This sideways force would slow the Earth up in the orbit, and it certainly would not have lasted the at least 3 or 4 billion years that it has been going around the sun. So that's the end of that theory.
Right, so that's his attitude. That's the end of it. You see, I say there's friction, the end. Because I say it's particles hitting particles and matter hitting matter, and that's the end of it. But again, it's energy hitting energy, and energy, there is no resistance to velocity for energy. There's just no resistance. Gravity doesn't affect gravity. Gravity doesn't really affect photons. It can't, because all the interactions are 100%. If it hits something head on, something's still going head on. Something's still going that direction. It can exchange directional information. It can't create directional information. And the fact that it can only exchange it means you can't change the fact that there's going to be so much quanta going that way. You can't stop the laser beam. And the fact that you could see that in light, that there is no resistance to light as it travels through space. It can hit things. It can hit matter. That'll create resistance. But there's no resistance in the space itself. And the very fact that we already know that would be an argument that whatever force was affecting this thing, these particles, that they have to be forces that don't affect the migration of quanta through the space. The space full of gravity obviously doesn't stop quanta, stop light, doesn't slow it down, doesn't frictionize it into nothing. It can't stifle its motion. And again, I'm just saying that if you're going to make a very dense field of particles, he should have been able to appreciate they could be particles like photons. And you could see that photons are not affected by the particle field. Alright, probably enough. Okay, till next time. I think we'll play this a little bit. Might be interesting.
It would be interesting and rather annoying. But what turns out to be true is that the more we investigate and the more laws we find and the deeper we penetrate nature, this disease, that every one of our laws is a purely mathematical statement in rather complex and abstruse mathematics. This is relatively simple mathematics. It gets more and more abstruse and more difficult as mathematics. And why? I have...
Yeah, so he's just talking about the fact that they're stuck with this formula because this particle thing doesn't work and there's no explanation, there's no model. And that's the joke of it, right? Is that all of these disciplines, all of this science, is all dependent on this one force and labeling it correctly, getting the model right. And that's the part where they left the building, so to speak. Be back. Alright, kind of a strange little bit. So he's doing a proof of what doesn't really have a formula, which is the rule that equal areas are swept in equal time, by gravity. So it's not even that that's a real formula, and yet he's doing a mathematical proof of it, and so he ends up relying on the geometry of it, so which goes back to Newton. So I just play this a little bit.
Incidentally, Newton made his proof geometrical like this, and made all his proofs in his book geometrical of this type. Today we don't use that kind of reasoning. We use a kind of analytic reasoning with symbols, which this kind of reasoning requires an ingenuity to draw the right triangles, the correct triangles, to notice about the areas, and to figure out how to do it, you have to be clever. But to have...
Yeah. Well, anyway, so we use symbols, and then the symbols just become completely unrelated to a reality because nobody knows that theta is the base angle of the right triangle created by these two vectors or whatever it's going to be, and that's where the math gets more and more convoluted because it loses relationship to something physical, some physical property, and that's sort of the problem with the symbolic mathematics. Be my argument. Concepts like sine, you take the sine of an angle, which is now taking a proportional length of one of the axes of the triangle instead of the angle, and that becomes somehow proportional to the angles proportional to the 360. So instead of it being an angle, it becomes a proportion. But anyway, what do I want to say about this? Yeah, I don't remember. There was some other point to make about this relationship between geometry and math, but I can't remember what it was. But let me see what he's going to say here.
And improvements in the methods of analysis so that one can be quite more stupid.
Right, quite more stupid. Anyway, yeah, so it really doesn't matter. So I'll just wait till there's a real subject besides just the idea of math. I'm not opposed to math at all. It's really good and all that kind of stuff, but yeah, it doesn't explain. It just diagrams in a out there kind of way. Alright, so we're back to inertia essentially, but the change in velocity that happens when you change the angular momentum, the circumference of a rotation. And so we'll play with that for a little bit, just so we do something. Yeah, so.
And they swirl around, and thus we can roughly understand the qualitative shape of the spiral nebulae. You can also understand in the same way, exactly the same way a skater spins when you start with a leg out, moving slowly, and as you pull the leg in, it spins faster because when the leg is out, it's contributing, when it's moving slowly, a certain amount of area per second, and then when it comes in to get the same area, you have to go around faster.
So again, he's going based on this area thing where the equal thing, and I'm saying that's a symptom of the condition. The speed change is creating the equal area, not the other way around. It's not trying to create an equal area. It's not increasing speed to accommodate the obligation to do an equal area. The increase in speed is just a consequence of the extra force you use to pull the thing in. So it's an extra velocity, which just increases the combined vector velocity. So the two vector velocities combined end up with an increase in speed in some new direction. That's a compromise between the two directions, the direction of pulling in and the direction of motion. So the two combine to just be a faster motion in a different direction. Yeah.
But I can prove it for the skater. The skater uses muscle force. Gravity is...
See, and then muscle force is really just, we're back to electricity and the charge effects. And it becomes sort of a nuclear thing in the sense that, you know, your heart beats because of ions on the surface of your heart, and the fact that they end up expanding and contracting the size of the molecules inside your heart, and it just creates this contraction, which creates contraction of the entire muscle fibers, which creates a contraction of the entire heart that squeezes. So it's electricity that's fundamentally not just triggering the event, but it's a kind of electricity that goes right to, again, to the nuclear products and creates a change in the atomic structure of the heart tissue.
It's a different force, yet it's true for the skater. Now we have a problem. We can deduce, often, from one part of physics, like the law of gravitation, a principle, which turns out to be much more valid than the derivation. This doesn't happen in mathematics, that the theorems come out in places where they're not supposed to be.
So I don't know exactly what that means, but the bottom line is it's all the same force. You just have to understand the mechanism it's disguised in or something. But it's, like I said, you're not going to be thinking about leverage and magnetism when you think about joints moving. But in a way, that's kind of what it is. It's that the electrical charge has a lot of force potential, and it's changing, stretching and contracting, expanding and contracting orbits and different things in the atoms themselves that are causing effectively a chain reaction that affects everything in the end. But it's all, the force has to actually travel through everything. For my hand to move, every bit of all the atoms in my hand have to have an application of those arrows, a force change that has to migrate through my entire hand to change the disposition, the orbits, the orientation of all of it. All of it gets changed.
In other words, if we were to say that the postulates of physics were the law of gravitation, we could deduce the conservation of angular momentum, but only for gravitation. But we discover experimentally...
Yeah, well, that they're all kind of connected. Let's see if he says that. You know, we discover experimentally
that the conservation of angular momentum is a much wider thing. Now, Newton had other postulates by which he could get the more general...
Right, so basically the point is that this again is just an example that there's evidences that all these forces have similar characteristics, not just the inverse square, but other similar characteristics. And I would argue that that's reason to take the idea of some explanation that would explain all of them seriously and not disregard it casually. But anyway, till next time. Alright, I guess I should have played this bit. I guess this is what I was. This is probably the bit I was saving this portion for.
Conservation law of angular momentum. But Newtonian laws were wrong. There's no forces. It's all a lot of baloney. The particles don't have orbits, and so on. Yet, the analog, the exact
So I don't know what that means. There's no forces. The particles don't have orbits. They do, actually.
Transformation of this principle about the areas, the conservation of angular momentum, is true with atomic motions in quantum mechanics, and is still, as far as we can tell today, exact.
So that's just more evidence of it, right? Is that it's the same mechanism, just expressed in a different granularity. Again, sand is different, you know, when you're close up and when you're far away. It means something different. If you're a grain of sand sand means something different than if you're a human looking at sand. And it certainly means something different if you're the earth looking at sand. You know, that kind of thing. Okay, now I think it's enough. Alright, this bit was a bit convoluted. Going through 3 different ways of calculating the same thing, a field theory, simple principle theory, and more Newtonian type theory. But anyway, and eliminating one, and then blah blah blah. But you know, I just use it for this. It doesn't. They're all using the same variables and just manipulating them in a different way to get the results. So again, it just demonstrates that you can sort of tailor math to come up with results, and some of it's more perfect than others. But first, you need the right principles to be able to weed out what only looks like a relationship.
But we can't tell ahead of time, without some intuition and guesswork, as to which is the best way to write it until we find out the new situation. So we must therefore always keep all of the alternative ways of looking at the thing in our heads. So the physicists do Babylonian mathematics.
Yeah, so I just liked it for that little point, that you got to keep this idea that there's different, you can start with a different foundation and come up with a different answer. So you got to keep an open mind, so to speak, and it just seems that physics has gotten really closed-minded over the last 100 years. Arguments like quantum mechanics is the most proven, blah 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 blah, science, the greatest scientific discovery in the history of mankind, blah blah blah, all that kind of overstatement has just corrupted its ability to say maybe there's a better starting point. So anyway, I don't know if there was anything else. This wasn't the best of the lectures, so yeah, it's a little bit of a grind to get through.
And pay little attention to the precise reasoning from fixed axioms.
Right, so I think fixed axioms are fine if they're really solid fixed axioms, but yeah, there's a lot of assumptions that are being called axioms. That would be the argument. The assumptions can get you into trouble. The assumption that because it looks like a tiger, it is a tiger, like in Australia or something. You know, I mean, there's organisms that look like they should be directly related, intuitive. They look right. They look like they're close relatives, but they're not. They just acquired the same shape, and it's those kind of things you gotta look out for. Yeah. So when a pattern looks similar, doesn't mean it is the same kind of thing. Anyway, I don't think there's anything else here, so we'll just see if there's anything towards the end. Alright, so he's doing a bit on, you know, the different ways of looking at things and the innate prejudices of our intuition or what we wish it to be and all that kind of thing. He's not using that language, but it's sort of a conversation about the difference between math being clinical, and our models being predictable in a more observational way. You can see it, and you can see where it's going.
That there is possible, and I've often made the hypothesis that physics ultimately will not require a mathematical statement, that the machinery ultimately will be revealed, just a prejudice like one of these other prejudices.
So there you also have a statement to the detractors. So there's an example where he's saying, yes, there won't be a mathematical solution, there'll be a model solution. So again, I'm arguing, I'm proposing a model. I'm not saying there isn't more math to be done. I'm not saying more math, making it more explicit, because I think there's better math to do. I think there's more explicit math that can be done once you know what the mechanism is. But clearly the mechanism makes the model, makes the math a redundancy. It checks the model, but it doesn't advance the model. The model is what you really want if you can get it. If you can get a model, you want it.
It always bothers me that in spite of all this local business, what goes on in a tiny, no matter how tiny a region of space, and no matter how tiny a region of time, according to the laws as we understand them today, takes a computing machine an infinite number of logical operations to figure out. Now, how can all that be going on in that tiny space? Why should it take an infinite amount of logic to figure out what one stinky tiny bit of space-time is going to do?
So we called it space-time, but let's just call it space and quanta.
I made a hypothesis often that the laws are going to turn out to be, in the end, simple like the checkerboard, and that all the complexity is from size.
So that's, again, a statement I've made. Made it before I ever knew who Feynman was. I've used the example of a domino flipping on checkerboards, that there's only a few things that these things can do, up, down, left, right, and it's sort of turning out that that's what we're stuck with. We're stuck with this quanta, this directional information, and all we're doing is collecting packets of directional information that is trapped, so it has no direction. We're basically taking quanta that has directional information and we're consolidating in packages or traps that have no directional orientation, substantially. Of course, if they're stretched, they have a directional net information, but they've taken away all the directional. They've made inert, made into potential, all the other directions. All the other directional information has no substance or reality. So it's kind of funny that the matter is essentially energy made inert. It's kind of taking something, the gravity, and turning it into nothing. It's almost the inverse of our perception.
But that is of the same nature as the other speculations that other people make. It says, I like it, you don't like it. It's not good to be too prejudiced about this thing.
So it is kind of funny that he likes that idea. He wants to see the simple, and yet he took an idea that was simple and he dumped on it. I mean, casually, without much depth of reasoning.
To summarize, I would use the words of Jeans, who said that the great architect seems to be a mathematician. And for you who don't know mathematics, it's really quite difficult to get a real feeling across of the beauty, of the deepest beauty of nature. C.P. Snow talked about two cultures. I really think that those two cultures are people who do and people who do not have had this, people who have had and people who have not had this experience of understanding mathematics well enough to appreciate nature once.
Okay. Yeah, it's all quite nice that there's relationships built into the geometry, but I guess there's a way of anthropomorphizing those relationships too as being bigger than they really are, because they're made of something so simple. So in a sense, you see that the Legos, you see the thing that's made out of the Legos, and then you realize the Legos are made out of Legos, kind of a thing.
It's too bad that it has to be mathematics, and then mathematics for some people is hard. When one of the kids reputed, I don't know if it's true, that when one of the kings was trying...
No, okay, I won't bother with that. King's stories are... Anyway, I'll be back. Alright, that's it for part 2. I don't know if there's much else to say. So, his real discussion was about the fact that it's sort of a preface to the next 2 videos, which I think will be, there will be a lot of math, but this idea that you have to do the math to see the relationships, because we can't see them because he doesn't have a diagram, a model. And so everything's seen through mostly the math, but it's math engineered in many cases. It's math where you find something that'll give you the answer. You find a way to relate the variables and create the right answer without understanding why those variables create the answer. You're just creating a formula and not understanding why the square root of the sine of some angle actually has a relationship that's relevant to where something ends up. And it's that component missing, where you just end up with formula math without any explanation for why the relationship described in the formula is real. Right, and then you end up contriving mechanisms to fit the math, a model that matches the math. Something like that anyway. I mean, you have math that predicts a result, and then you you create models that'll attempt